Have you ever wondered why some sets of information create only one possible triangle, while others allow for different possibilities? Let's break it down and explore why some triangle congruence rules always works, while others don't. I'll be using straws to represent the sides and arc sectors to represent the angles. Let's go through each scenario one by one. For SSS, if I give you 3 specific side lengths and asked you to construct a triangle, there is only one way to connect them. No matter how you arrange the sides, they must always meet in the same way to form a unique triangle. Since there's no other way to draw a different triangle with the same 3 sides, SSS always guarantees congruence. Now let's try forming a triangle using only 3 angles. At first, it might seem like we can just align the angles and call it a day. But here's the problem. I can spread the angles further apart or closer together, making larger or smaller triangles that still have the same angle measures but different side lengths. Since the triangle size isn't locked in, AAA does not guarantee congruence. For SAS, we're given 2 sides and the included angle between them. When I place these 2 sides with the given angle, there is only one possible way to complete the triangle. The third side must fall into place exactly as expected. This is why SAS always creates a unique, congruent triangle. Now let's test SSA, sometimes called side-side angle. Since the angle is not included between the 2 sides, it might seem like it should work. But here's the issue. I can keep one side fixed while swinging the other side to create 2 different triangles, one wider and one more narrow. Because we can get 2 different results, SSA is not a valid congruence theorem. Here we're given 2 angles and the included side between them. Since the angles are locked in place, there is only one way to connect the third side. This means the triangle shape is fully determined, ensuring that ASA always guarantees congruence. This time, we have 2 angles and a non-included side. At first, it might seem like this leaves room for variation, but since the angles are fixed, the side must always connect in a specific way to maintain the triangle structure. Because there is only one way to complete the triangle, AAS guarantees congruence. Finally, let's look at HL, which applies to only right triangles. If we know one leg and the hypotenuse, we can prove the missing side using the Pythagorean theorem. At first, you might wonder if this behaves like SSA. Shouldn't I be able to swing the leg around to form 2 triangles? The answer is no, because the right angle locks the structure in place. Even if I swing the leg, the only result is a reflection of the same triangle. Since the Pythagorean theorem forces the missing side to be a specific value, HL guarantees congruence and is essentially an indirect case of SSS for right triangles. So we've explored why some sets of information force a unique triangle, while others leave room for variation. Side, 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 angle, side, angle, side, angle, 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 side, and hypotenuse-leg always works. Angle, 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 and side, side angle do not guarantee congruence. Triangle congruence isn't just about memorizing the theorem. It's about understanding why they work. Next time you see a triangle problem, think about what information you have and whether it's enough to guarantee a unique shape.